Hello, welcome to Space. This is the third part of the lecture, Sequential Circuits, Analysis and Synthesis. In this lecture, we will be talking about registers, mainly about registers, universal shift register, and finite state machine, its analysis and synthesis. I am Chandra Chandran, MTech graduate from IIT Bangalore. I am working as a senior engineer at Calpron. First, we'll be seeing about registers. Registers are blocks which store data in microprocessors mainly. Mainly you can see in microprocessor, microcontroller in the CPU section. You can see registers which store data temporarily. When the power goes off, the data goes off. So it is a non-volatile memory, and it is made up of flip-flops. And there's a cascade of flip-flops, and the bit gets shifted to flip-flop with respect to clock pulses. That is in a shift register. The binary value gets shifted by one flip-flop to another flip-flop with respect to clock pulses. So depending upon the manner in which the data is entered into shift register and the data is retrieved, it can be classified into four types. That is, first one is serial in, serial out. Second, serial in, parallel out. Third one, parallel in, parallel out. And fourth one, parallel in, serial out. So this is a serial in, serial out register. Here you can see it is made up of D flip-flops and cascaded. All the flip-flops are cascaded to each other, and the output of one flip-flop is connected to the input of next flip-flop and goes on like that. And here you can see we are taking a 4-bit data, and so there are 4 flip-flops. If you are to n-bit data, there will be n flip-flops, and this is a serial input where the next state of D flip-flop is the present value of the input data. So if you want to enter a data 1011, then we will be first entering LSB at the MSB bit. That is here this bit. At the third bit we will be entering the LSB, that is 1, and then 1, this one 0 1, like that. So it goes on like this, 1 1 0 1. And so you can see here at the 0 clock all are 0. At the first clock Q3 equal to 1. At the second flip-flop, this first the first bit gets shifted to second bit, and you can see it becomes 1 1. And third clock pulse it is 0 1 1. At the fourth clock pulse it gets stored, and all the 4-bit data gets stored, that is 1 0 1 1. Next one is serial in parallel. The structure is the same, but we are taking the parallel out. That is, we are taking from each flip-flop output. So you can see here in the earlier one we are taking the serial out. Here we are taking the serial out from the LSB, but here we are taking the parallel out from each flip-flop. So data is entered in the same manner and is taken from each flip-flop in order. That is, this order is MSB to LSB. So you can see here we are entering the data in the same manner 1011, and we are taking the parallel out from each flip-flop. And here you can see parallel in, parallel out. Here it is not cascaded, but each bit is stored in each flip-flop parallelly. So we'll be entering parallelly the data, that is D3, D2, D1, D0, and taking the parallel out, that is Q3, Q2, Q1, Q0. So this is a parallel in, parallel out parallel out register. And next one is parallel in, serial out. Here the circuit is bit complex, not complex, it is much more bigger. This is a 2:1 mux buildup of AND gate and OR gate. These three are actually 2:1 multiplexer, where at the 0th bit there will be loading, that is will be loading the data from data parallelly, that is D3, D2, D1, D0, and at the when the binary value is 1 at this end, will be shifting the data, that is this is connected to one. The output of first flip-flop is connected to this input of second, and it goes on like this. That is at the shift logic. So when the load is equal to the shift bar load, that is this input, when this input is equal to 0, so here there is a inverter, so it goes 1, and this AND gate get enabled and so it is a loading process. So it is, and the parallel data here gets stored in the flip-flops at next clock pulse, and when it is shifting, this value, this input is equal to 1, and these AND gates are enabled. So then at that time the previous input, the previous output, that's this flip-flop output is connected to the input of next flip-flop. This output is connected to the next flip-flop. So it goes on like this. So it gets shifted to each other. So it acts as a shift in shift out register. See, serial in serial out register. So this is a circuit of universal shift register where all the combinations of shift registers happens in one circuit. Here there is a 4:1 max which selects the circuit connections for different combinations, that is for serial input parallel out, parallel input serial out, parallel in parallel out, and serial in serial out. So when this is the S0 S1 inputs, select inputs of the multiplexer, and when S0 S1 equal to 0, the output of each flip-flop is connected to the input of those respective flip-flop. So here you can see at the A3 end, this output is connected to the input of the same flip-flop. So the value becomes no change. At this, whatever clock pulses go through the flip-flop, the value doesn't change. So it is a no change state. And when it is 0, 1, the shift right mechanism takes place. That is, we can the bit gets shifted from A3 to A1, A3 to A2 to A1, and then to A0. That is a shift right. And when it is 1, 0, that is S1 S0 equal to 1, 0, then it becomes serial input for shift. That is, it does left shift happens in the shift register. That is, A0 data comes to A1, A1 data comes to A2, A2 data comes to A3. That is left shift. So when S0 and S1 equal to 1, 1, then it is a parallel load. So you can see here, this is the input for the parallel load. Its I3 becomes stores at this A3. That is, each bit at the each portion loads the universal shift. That is a parallel load condition. So this is a function table. Mode control, you can see S1, S0, there is a select lines of the multiplexer, and the register operation is no change, and then it is shift right, and this shift left, then last one is parallel load. Next topic is finite state machine. What is finite state machine? It's a single sequence circuit where there are a group of flip-flops, and the output of this group of flip-flops is called the states, and where there are some inputs to the FSM, and according to these inputs there is a change in particular states, or there are state transitions of these flip-flops in a particular order, and they also generate outputs to the system inside and outside the system. And the whole digital circuit is called the finite state machine. And what example we can see is, as we discussed in the previous lecture, that's a counters. The counters are also called also a type of finite state machine, where there are some inputs to the counters and causes state transitions and outputs also. And another example is interior of a microprocessor or a microcontroller or a CPU, where there are many registers, where data holding registers, and there are many data path operations. These operations are controlled by a control unit inside the microprocessor, and this control unit is a example of FSM. And also there are many other examples of FSM, and actually there are mainly two types of FSM here. One is Mealy machine, and another one is Moore machine, and they both differ only in which the outputs are generated. We will be seeing in the next coming slides, and also in the coming slides we will be seeing analysis of an example finite state machine, and also we will be designing some 2 or 3 finite state machine with different type of flip-flops, and these will ready to have a good clear picture of the FSM to you. So this is the Mealy machine. So this is flip-flops, and the output of flip-flop is called the state, and present state is the value of the flip-flop outputs at the present clock edge. and this is the next state logic, which is a combination circuit which generates the flip-flop inputs for the next state transition. So this will be the next state logic will be a function of inputs and present state, and this output logic is another combination circuit which generate the outputs. So in a Mealy machine, the output logic is a function of inputs and present state. In a Moore machine, it is not like that. We'll be seeing that. So there's the output, and the flip-flop contributes to states. The value of the flip-flops is called the present state, and it goes to transition from one state to another according to the next state logic. So this is a Mealy machine. Next is a Moore machine. Here the output are synchronous. In the earlier one, the Mealy machine, the outputs are not synchronous because the outputs were function of input. In the inputs are asynchronous to the clock. So in the Mealy machine, the outputs are asynchronous. In a Moore machine, this is a present state made up of flip-flops, value of flip-flops, and the outputs are a function of present state only. Here you can see it is not a function of inputs, which are asynchronous values. And the next state logic again is the same as Mealy machine. The next state logic is the function of inputs and present state. So this is a Moore machine. Only the difference is outputs are synchronous. In a Mealy machine, the outputs are not synchronous. So we'll be analyzing one final state machine in order to understand what is a FSM, or what is a synchronous sequence circuit. So we have already defined FSM. It is some inputs and some flip-flops and some outputs which generates which is a function of present state of flip-flops or the inputs according to the Mealy machine or Moore machine. The analysis starts from a circuit diagram and culminates in a state table or state diagram. In an analysis, we will be analyzing we'll be getting a circuit diagram, which is circuit diagram or logic diagram, which is that will be a synchronous sequential circuit, and we will be deriving to a state table or state diagram in order to understand the working of the finite state machine. So there are flip-flops and combination circuit to produce flip-flop inputs and generate outputs. The behavior is determined from inputs, outputs, and state of its flip-flops. The next state and outputs are both a function of the inputs and present state. Only according to Mealy and Moore, it varies. It is possible to write Boolean expressions that describe the behavior of the sequence circuit. So next we do an analysis of an example sequence circuit. So in order to understand that, we'll be seeing an example sequence circuit and analyzing it. So this is the example FSM. This is the FSM. This is made up of D flip-flops. There are two flip-flops, A and B, and these are the combination circuit which generates. This is a combination circuit which generates the output Y. This is the input X, and this is a next state logic. This is a next state logic which derives the flip-flop inputs in order to know the next state or the state transitions. So we'll be first writing the state equations according to the circuit diagram. The next state as a function of present state and inputs. A t plus 1 is the next state of A flip-flop. That is, you can see from here, it is AX plus BX. You can see here D input of A flip-flop is D flip-flop is AX plus BX, and this is the next state of B flip-flop. That is, you can see A bar X, and output as a function of present state and inputs. That is A plus B, this is A plus B here, A plus B into X bar. So here you can see the output. You can see here this is a function of inputs and present state. So it is called a Mealy machine. This is a Mealy FSM. So we can make a state table for the time sequence of inputs, outputs, and flip-flop states. So this is A and B flip-flops. The present state is a present clock edge, which shows the present state or the present value of flip-flop. This is the next state of the flip-flop. So it is there 0 0. You can see here. From according to the state equations, we can derive the state table. This is I'm not reading the state table. You can understand by looking at it. We can understand the state table. So this is a state diagram that is according to the state table. So this is a Mealy FSM. That's why there are input and output. This is 0/0 is x/y, that is input slash output. So you can see this is a state diagram. This is a value of the state, that is S0, S1, S2, S3. It is 0 0 0 1 1 0 1 1. So when it is the flip flop is at state 0 0, and when the input is 0, the output becomes 0, and it is in the same state. So when input is at the 0 0 state, and when input the state flip flop value is 0 0 and the input is at 1, the output becomes 0, and the state flip flop changes the value from 0 0 to 0 1. So like that we can see all the combinations of the state table. That is from 0 1 when the flip flop is at 0 1 state, and when the input is 0, then the output becomes 1 and the flip flop states changes to 0 0. Like that we can see all the combinations of the state diagram. You can see here, we can look at it and you can find out all the values, all the flex state transitions of the flip flop. So these are the flip flop input equations. Since we are using a D flip flop, the next state is the value of the present D input of the flip flop. That is dA equal to AX plus BX, dB equal to A bar X. So this is as I told earlier, this is a Mealy state machine. So in order to analyze the circuit, in general, flip flop input equations for different ones are solved as follows. That is, the FSM made up of D flip flop, the next state equal to the D input. For JK flip flop, it is J Q bar plus K bar Q. For T flip flop, it is T, that is present input T, XOR with present state Q, that is the next state. So before going into design of FSM, we can do some state reduction and state assignment. The reduction of number of flip flops in a sequence circuit is referred to as state reduction. So the states are actually the flip flops. In a counter, we are the values of flip flops are also important as in a counter, but in a FSM we are interested only in input output sequences. So we can reduce the number of states. We can merge some states which are equivalent. If there are some states which are equivalent, we can reduce it or we can merge it. So the reduction of number of flip flops in a sequence circuit is referred to as state reduction. So we can reduce the number of flip flops like that by reducing the states. The intent states are merely to provide required sequences. So we are in FSM we are interested only in the input output sequence. The internal state can be reduced. So we will be considering one state diagram, an example state diagram. According to consider the input sequence like this: 0 1 0 1 0 1 1 0 1 0 0. So according to sequence, there is some state transitions, and we can analyze the state diagram, and we have to reduce the states. That here there are 7 states. If we can reduce to 5 states or so, we can reduce the number. We can reduce the number of states and the complexity of the circuit. So this is the state, this is the input, this is the output. So by analyzing the state diagram, we can see we can form this table. So 2 sequence circuits are said to be equivalent such that if identical input sequence are applied to both circuits, the identical output sequence are obtained from the both. So like that. So it says that if there are two sequence circuits and these two sequence circuits are said to be equivalent, if identical input sequences are applied to both circuits, and we can produce identical output sequences. So that is, if the two circuits are different states, if the two circuits are different states but the input and output sequences are same, then the two sequence circuits are same. So the number of states can be reduced in a sequencer without altering the input output sequence. Only by reducing this number of states we can make a sequence circuit. We can reduce the complexity of a sequential circuit. So step one is, first state table is formed. This is the state table of the shown example state diagram. You can see here. See, these are state transitions. You can see present state, the next state A, B. See, if you can see here, see present state E and G. The next state are same, A, F, and the output is also same. So we can merge these two states together. And again, here you can see D and F, E and G. We have found out that is equivalent. So again, we can see here there are coming to the same outputs. So here we can again reduce these two states to 1. So here there's a statement here. Two states are said to be equivalent if for each member give exactly the same output and send the circuit to the same state or to an equivalent state. That is shown here. See here, E and G, the same state, and here D and F, it is going to same equivalent state with the same output. So we can reduce this two states to, we can merge these two states to 1. So from the above table sheet, E and G and equivalent. For E and G and x is equal 0, x is equal to 1, they both go to the same A and F respectively. So here we are reducing it. This is the first reduction where G and D are made to 1. We have replaced G by E, and now observe D and F equal. See here we have changed this to E to G to E. We have replaced G by E, and now observe D and F are equal. Now here these two states are same, where the next state is E and F. So now observe D and F are equivalent. Now again replace F by D. So second reduction, replace F by D. So you can see here there are only 5 states. So the circuit complexity is reduced here. This output sequence is exactly same as obtained for the given state table. So here this is the reduced state transitions, and this is a revised state diagram. So you can see instead of 7 states, there are only 5 states here. If you design the circuit, we can reduce the complexity of the circuit to a smaller one, simpler one. Now we can see a state reduction by implication table. An implication table is a table which shows all the combinations of the state present states and then the next state transition. So consider the same example of 7 states. This is a 7 state example, the 7 state table. And formation of implication table. The table consists of squares placed in the intersection of a row and column where two states can be tested their equivalence. The table gives all the possible combinations of two states. The next step is put a cross in any square corresponding to a pair of states whose next state and outputs are not equal. So in the example, these states are combinations where the outputs or the next state are not equal. So then put a tick in any square corresponding to a pair of states whose next states and outputs are equal. In the example, we can show here according to the earlier steps, you can see GE are the equivalent states, DF again are the equivalent states. So these GE can be, we can put a tick across it, and again at the combination D and F combination we can put a tick. So this is the implication table. You can see here these are all non-equivalent states. This put the cross tick cross mark squares are all unequivalent states. Here you can see D and F equivalent, where the next state is G and D. Again, G and D also is a equivalent state. We are put a tick mark here. And these AB here, AC, BD are the next state. So these are the next state of the AB. So here you can see it is AB implies AC, BD, and AC implies BD. You can write like this. And here you can see D and F are equivalent and G and D are equivalent. See, you can see here in this example, you can find the equivalent states here, D, F and EG. So this is step 4. A square in the table is crossed off. It contains at least one implied pair that is not equivalent. For example, square defined by B and A is crossed out as it contains pair BD which are not equivalent. And this process is repeated until no additional squares can be crossed out. Finally, all the squares that have no crosses are recorded with tick mark. The square with check mark define equivalent states and those with cross mark define inequivalent states. Just simple. Where the squares with check mark define equivalent states and those with cross mark define non-equivalent states. So in this, equivalent states are DF and EG. So this is an implication table shown again for a clarity. So these DF are equivalent and EG are equivalent. So this is a reduced state table where the state F is replaced by D and G is replaced by E. So we have from 7 state, we have reduced the state number of states to 5. So the complexity of the circuit will be reduced. So this is the finally reduced state table. You can see here. So next is state assignment. The process of assigning coded binary values to states is called state assignment. So suppose there are 5 states. So 5 states we can make a 3-bit binary assignment, that is 2 raised to 3, 8. We can hold 8 states for that. So we can do 3-bit binary assignment, that is for state A it can be 000, next you can 001, 010, 011, 100. If there are again much more states here, we can give that 101, 110 like that. We can also give gray code. That will be easy for the circuit design if we have a gray code assignment, and one hot assignment that depends according to the application. So for M state, the code must contain n bits, that is 2 raised to m, that is for the binary assignment. That is this is the case. So if there are unused states are treated as don't care conditions during the design. Don't care conditions usually help in obtaining a simple circuit, much more simpler circuit. So let us now enter into FSM synthesis. So we will be designing some FSM, very small FSM. So this is a design procedure. For step 1, from the word description or from the problem definition and specification of desired operation, derive the state diagram. So from the word description or from the problem definition, we are deriving a state diagram and reduce states necessary according to the state reductions we have shown earlier, that is by implication table or by state tables. And next, step 3 is assigning binary values to states. That is, it can be any, you can select any of the state assignment, that is binary assignment, gray code assignment, one hot assignment, etc. And step 4, obtain binary coded state table. From the state diagram we can derive the state table. And step 5, choose the type of flip-flop to be used. Usually for a JK flip-flop the circuit will be much more simpler, but for a D flip-flop we can design a big circuit also in a easy manner, because the next state of the D flip-flop is very easy. And next is step 6, derive simplified flip-flop input equations and output equations using K-maps. And finally step 7, we are drawing the logic diagram or the synchronous sequence circuit. The final diagram that is a result, that is a logic diagram of the given problem. So first we will see a sequence detector. The problem is to detect 3 or more consecutive ones in a string of bits coming through an input line. So this is the block diagram of the sequence detector. There is one input X and output Y. This is the clock given to the FSM that will be entering into a flip-flop clock. So to detect 3 or more consecutive one. So here there's a serial bit stream. It will be coming and coming. So as it comes, we have to count the number of ones, and if there are 3 or more, the output should be 1. That is the problem. That's a given problem. So from the given description, number of ones number of inputs equal to 1, number of states 4, number of outputs 1. So number of states it is 4, because at the first state it will be it is a standby state, it will be staying there, and next if there is a 1 it goes to next state, and next if there is a 1 it goes to next state, and next state equal to 1 it goes to next state. So there are totally 4 states and then remains there, and if again there are 1 coming, it will be staying there, and otherwise if there is a 0 it goes again to the first state. That is the logic, and this is a Moore model FSM, because the output does not changes with input, and it's not a function of input value. So according to the state, so when it reaches the fourth state, the output becomes 1. So that's why it is a Moore model FSM. So this is a state diagram here. So there's a first 0 coming here, so it will be in the same state. And the first one comes, it goes to the next state, and the second one comes, it goes to the next state, and there's a third one comes, it goes to the next state, and the output becomes 1, because there's a three we are counting 3 consecutive ones, and again there if a 1 comes there, it again remains there, because there's a fourth consecutive one, it remains there, so value will be 1, and then if there when a 0 comes here, it goes to the initial state and remains there. Again the logic comes, and in the other case, if it goes to 1 to the first state, then if a 0 comes, it goes to the initial state once again, and there is 2 ones come here, and again then when a 0 comes, it again goes to initial state, like that. So you can study it, you can analyze it, and find out whether it is the working in the same manner. So let us now assign binary values to states, that is S0 equal to 0 0, S1 equal to 0 1, S2 equal to 1 0, and S3 equal to 1. This is the binary assignment, and this is state diagram. Sorry, the state table according to state diagram logic. So there are present state AB, next state AB, input X, and output Y, and we can easily find out output here, because the output is a function of present state only, that is in a Moore FSM. So that is AB. You can directly find out from here, that is Y is equal to AB, A into B. And now you can see this is a present this is the next state here. So this is a transition according to input given here. So let us now do the synthesis using D flip-flops. The flip-flop inputs are as a function of present state and inputs, that is next state of A flip-flop is a function of present state AB flip-flop and input X. Next state of B flip-flop is a function of AB and X, and outputs as a function of present state, since it is a Moore machine, that is Y is a function of A and B. So to derive the flip-flop input equations, consider below excitation table for state transitions. So this is the excitation table for D flip-flop. So when the present state, this is the present state, and this is the next state, and this is a D input. And if the present state is, if the state is changing from 0 to 0, then input should be 0. If it is changing from 0 to 1, then input should be 1. If it is changing from 1 to 0, the input should be 0. If it is changing from 1 to 1, then it is 1. So the D input is actually the next state only. This is equal to the next state of the flip-flop. So this is the next state, present state, next state, and the flip-flop inputs. It is shown here. You can see, you can look over it. And these are the K maps. This is the input of the this is the value for dA, that is the D input, that is AX plus BX, dB AX plus B bar X. You can find out from here, from the K map. These values are 0, so Y equal to AB. So this is a required circuit. So this is a required circuit of sequence selector using D flip-flops. Now we can use the synthesis or design using JK flip-flops, and this is a excitation table for JK flip-flop. So this is here written here. To derive the flip-flop input equations, consider the below excitation table for state transitions. Suppose this is the output, this is a present state to next state transition. If it is 0 to 0, J and K should be either 0, 1 or 0, 0. So it has become 0x. And for state transition 0 to 1, it can be 1, 1 or 1, 0. It can be set state or complementing state, that is 1, 1, 1, 0 or 1, 1. And again, next is from 1 to 0, it can be 1, 1 or 0, 1. And finally, we have present state 1 to next state 1. It can be 0, 0 or 1, 0. So it becomes x0. So that is the logic here. And this is state table. These are the flip-flop inputs according to present state and next state. These are output. Output doesn't change because that is the same for all flip-flops. So this is the input equation according to K map. 3 variable K map. You can see here if you are JB, KB, Y doesn't change for flip-flop. So this is a required circuit of the sequence generator using JK flip-flop. Again, there are 2 flip-flops, so it is much more simpler. This is output equation, output circuit. So next is synthesis using T flip-flops, and this is excitation table like JK and D. So this is a state transition. So for 0 to 0, it is a non-complementing state transition. So Tn will be 0, and 0 to 1 it is complementing. So Tn equal to 1. 1 to 0 again it is complementing. So it is 1. 1 to 1 there is no change. So it is 0. So this is the state table. So that next this equation for the T input. A flip-flop for the T flip-flop, the B flip-flop. So here we have got A bar B plus BX bar plus BA bar X. This we are combined and used B XOR X, that is this is B XOR X, that is A bar B plus B XOR X. This is the output equation that doesn't change. So this is a required circuit. So with T flip-flop, the circuit complexity are little bit increased. So this is maybe depending upon applications, you can use D flip-flop, JK flip-flop, or D flip-flop. I think better recommend D flip-flop for all the synthesis, because that is easier to design and the circuit is not much complex or not that much simpler as JK flip-flop, but it is moderately simple. So next circuit is next FSM is serial complementer. Serial complement, that's it. Two's complementer FSM serials two's complement. Earlier you might have seen a combination circuit which does a two's complement for a combination circuit. But here we are using serial complement. The input, this is a block diagram for that. At the input, a stream of bits come. Suppose this is an 8-bit complementer. So MSB comes first. That is the logic here. LSB comes first. So and as it goes through, the output at the output the two's complement output comes from the at the output Y. So we will be finding the logic of the two's complementer. this is the input. If this is the input, that is 0 0 0 1 0 1 0 0, the output is 1 1 1 0 1 1 0 0. The logic for the 2's complementer, serial 2's complementer, you can see like this. At the MS, starting from the LSP, it is 1 is 0 until it reaches the first one. The value will be non-complemented. After that, after it reaches at the 1, at the next bit, it will be complementing. So there will be only two states. One state will be uncomplementing, and the next state will be complementing all coming serial for all incoming bits. So this is written here. If you look from LSP to MSP until it reaches the first one, it is uncomplemented. After that, it is complemented. Just it takes a opposite value, that is 1 to 0, 0 to 1, like that. So in a serial complementer, LSP comes first. So according to logic, the state diagram is shown in the next page. So it is a Mealy model FSM. You can see that. See here, this is the first state. When it is 0, it does not do any complement. It does the same output as the input. And here it is 0 bar 0. You can see it. It is not complemented. And when it reaches the first one, at that one, that doesn't complement, and it shows the same value 1. That is 1 bar 1. And then when it reaches the S1 state, that's the next state, it complements all the input coming bits, that is 0 to 1 and 1 to 0. This is a complementing state. As it goes through any value, any number of bits, it will be complementing and complementing. So that is the logic. So we can derive a state table. So this is a binary assignment, that is S0 equal to 0, S1 equal to 1, and we can do a synthesis using D flip-flops. So this is a person state input, next state flip-flop input DA, and output Y. Here it is, the output is asynchronous. So it is called it is a Mealy FSM. So DA A plus X, Y A bar X plus AX bar, that is AX or X. So this is a required circuit. This is the output. This is a equation for flip-flop input, that is A plus X. So this is a circuit. So again we can use a synthesis using T flip-flop. Let us see what will be the complexity. A bar X. Just a little bit A bar is came, and A bar has come. That is a little bit but since we have a bar at the flip-flop output, it is okay. So this is a required circuit with T flip-flop with design, used for design. So next, this is a third example of the FSM, that is sequential parity checker. So what is a parity? Odd parity means number of ones in a bit sequence should be odd. That is for a 8-bit data. Suppose for example, for a 8-bit data, number of ones in the bit stream is, if there are number of ones in a bit stream is odd, then it is called odd parity. And if number of ones is even, then the parity is called even parity. So here we will be designing a sequence circuit to check odd parity in a serial sequence. And here it is a Moore model FSM. So why it is a Moore model, we will be seeing that. So this is a block diagram, and the input stream will be coming. Suppose a 8-bit input stream is there, and if it is a odd number of if there are odd number of ones, the output will be odd. If there is a odd number of ones in the bit stream, then the output will be 1. And if there is a even parity, and the output will be 0. This is a clock here to the flip-flop of the FSM. So let us try here. Let us see here. This is state diagram. This is the first state. This is the second state. So when x is equal to 0, it is in the same state. When there is a 1, that is number of ones are odd, it goes to the next state, and the value output becomes 1. That is the output at this state, it will be 1. And x is equal to 0. Again, there is, if 0 comes, it remains there. And if there is a one more one, one more x equal to 1 coming, then it changes to the, it goes to the initial state, that is it comes to the even parity. And simply how to explain the working is, at this state it is showing a even parity, at this state it will be showing a odd parity, and when it's a odd parity the output will be 1, at even parity output will be 0. So that is the logic of the state diagram, that is the working of this state diagram of the circuit. Let us now do the further synthesis. So this synthesis using T flip-flop. This is the present state, input, next state, flip-flop. According to state diagram, we have drawn here the state table. So these are flip-flop inputs. These are output. And the KMFs, T equal to X, Y is equal to A. So this is a T flip-flop. A simple T flip-flop shows a parity checker, that is odd parity checker. So this is like no gate, only there's a flip-flop here. So this is a final circuit. So that's it. We have seen all the synchronous sequential logic examples and all the process for it. So next, the fourth part will be coming, that we will be taking on asynchronous sequential logic and metastability. So until then, bye. So please like and share the video, subscribe the channel. Thank you. If you have any doubts or comments, you can mail me to chanch484@gmail.com. And if you have any doubts or questions or comments, you can put at the comment section of the video. Thank you once again. Thank you.